Okay, folks. So, how's lab 3? I heard great and I heard terrible. That sounds about right. That sounds about right.
How about in the middle?
In the middle. Okay. So I will remind. So Wednesday afternoon, people have a lab this afternoon. Anyone that wants to come work on lab 3 this afternoon, I'll be in the lab from 1:30 to 4:30. There's also a lab section tonight from 7:30 to 10:30. That's the one that we share with 2300. So that one's a little steamy, but you're welcome to come to that one as well. There's also a lab section tomorrow, 1:30 to 4:30, and Friday, 1:30 to 4:30. So lots of opportunities this week to come work on your ARM. Any questions? Any lab 3 questions? Any final project proposal questions? General questions about the proposal? Maybe not necessarily specific ones about your project. So this is something that I've been thinking about. Bruce and I have been talking about this. And I wanted your opinion on this. What I'm thinking of doing is offering a reward for demoing your final project early. And the amount of bonus points that you would receive for demoing early is non-linearly related to the amount of days early that you've demoed. So in particular, it's going to be driven by this logistic curve, where if you demo, 1, 2, or 3 days early, you get 1 or 2 points. Probably not worth it. However, if you demo, a week early, you're looking at, 7 up to a maximum of 8 bonus points for demoing early. Yeah.
So is your demo date like your last lab, or is it going to final exam?
Your demo date is, I'm going to set up a spreadsheet for people to sign up for their demo time in the next week or so. But for everyone, it'll be in about 4 or 5 weeks from now, and it's generally before final exam season. Your lab reports then are due. Your final reports are due on a date that is dictated by the university, and that I think is posted on the course website. That's into final exam season.
That's okay.
Yeah. There is not a final exam for this course. They're just final demo. But how should you think about this? So why consider doing something like this? There are a few reasons. One is, in the real world, there is usually some benefit associated with finishing your projects early. So to the extent that this class is meant to simulate those sorts of environments, this is a nice simulation of that. Yeah. You just get more work if you finish early. Sure. Okay. Well, you won't in this case. But this, I'm encouraging you here to try to actually do a little bit of a trades. What am I trying to say? You're trying to optimize a few different things here, right? Because here's an opportunity to get some bonus points. But one of the things that you're evaluated on for your final project is its complexity. So is it worth it to demo early and lose the extra days to add additional complexity to your project? I don't know. Maybe for some of you it is, or maybe for some of you it's not. Yeah?
So do we do demo in class?
So the way that the demo generally works is, with your permission, we'll film it. If you don't want that, that's no problem at all. But the way that it typically works is we go to the lab together and sit down at your lab bench. And in 5 or 10 minutes, you talk me through what you built, why you built it, how it works, and show it off. And the demo is basically a conversation between your group and my group, where I ask you some technical questions about it. By no means trying to trip you up or anything, just to elicit what you were thinking as you were building this thing, and then you show it off. And then you get, so the demo is quite conversational. The final report is tremendously detailed. So all of the real detail associated with your final project would go into that report, which takes the form of a web page. I think you're all aware. You'll all make a web page for your final report. Yeah. Out of 100, yeah. That's a good question. I think that's going to be relative to the day that you sign up for. Everyone will demo within a day of each other, right? So 4 or 5 weeks out, I think that's close enough to call that everyone has the same amount of time starting from now. As the deadline approaches, people will argue with me about that, but make it known you agree with me right now, okay? Yeah. Oh, I don't know. I don't know. Yeah.
Like usually when you get a product out before your competitors, like you can get the edge in the market. So like pretty much every single day that your product is out is extra profit that you're making. So like the more that you cut your development time, the less you have to pay for like labor costs
Sure.
and development like it's just and like it's like every single day that you can sell a product is a day that you are making money. So if you're planning on like making some really high-end product that like you're gonna sell a ton, you could be making up to like $200,000
Sure.
a day.
Sure.
And like,
So what does this mean? Well, so throughout the final project, as we talked about last time, usually it's the case that we'll stop doing these lectures. And in lieu of lecture, we'll meet together in lab more often so that we can help you complete your final project. But when you start thinking about your final project, you need to be very careful about planning. There's a lot of autonomy associated with this project. You are responsible for setting a schedule and meeting that schedule. That being said, I'm going to sit down with each group every week and ask for a status update, right? Because I want to make sure that things are moving along at an appropriate pace. So decide what the ultimate outcome, decide what you want for the ultimate outcome to be. What are you trying to build? And then you and your group should construct yourselves a schedule and try to stick to that schedule to the best of your ability. So there should be certain hours of the week, every week, where you say, we will be in lab working on this. That's obviously going to include your enrolled lab sections. And then when we transition these lecture times to additional lab times, clearly you're all available to go into the lab at these times, right? Because you're all here. So there's going to be lots of opportunity to be in the lab and lots of opportunity to get help. But it's going to be up to you to be quite autonomous with this. Yeah.
Will you open the lab on different days?
Yeah, I can talk to your, I don't promise I'll be here those days, but I can talk to your TAs and we can likely get the lab open. I cannot give card access for this class. I'll confirm that and make sure that's rule. I believe that's still a rule. So I can give card access for this class. Those of you that take 5760 next semester will have card access so that you can get in there and work with the FPGAs. Okay. Also, on the topic of final projects, many of you are proposing, so final project proposals are starting to roll in. I got the Wednesday afternoon, a lot of Wednesday afternoon peoples already, and then some more continuing to roll in. If you are buying, if you want to buy stuff for your project, sensors, motors, whatever it may be, I am going to make a purchase on, I will make a purchase on, let's say, I'll put a date on Canvas. It's going to be sometime next week, probably Wednesday or something. But what I need from you, if you're buying anything, is very, very specifically what you want bought. So I want the part number and I want a link to the page from which I should click and add to cart, because I want to buy very, very specifically what you want. So I've seen some proposals where people are specifying things that they need that are a little bit general, and for now that's okay. By the time the order deadline comes around, you need to send me a link to the specific item that you want bought. Yeah. So the total cost of your project, which includes stuff that you buy and stuff that we will buy for you, should not exceed, I'll double check the limit, but I believe it's $125. So that means the sum of everything that is bought by both you and me should not exceed $125. That limit exists so that people don't go out and buy like a small car and then, you know, we have to have this limit in place. So it shall not exceed $125. What percent of that will I pay? I need to double check that limit as well. I believe it's usually about 50.
Like you'll pay up to 50?
Yeah.
So it's not like we pay 50%.
That's correct. That's correct. I'll pay, and I'll double check that what that limit is. I believe it's 50, but I will double check what that limit is. Yeah.
When I saw on the course website, like part of the agreement was that your cost would be under 25.
Yeah.
So that included like the big board.
You should budget all that in. Yeah. If you built your big board, you get to keep your big board. Any person that built their own board gets to keep that board. Yeah.
So the final project, is there going to be like smaller board that we can use? Maybe, for example,
Yes.
we want to design our own breakout board so to accommodate a smaller project.
There is, I can give you one, but we have a smaller version of the breakout board for the PIC32 that includes only the microcontroller, breakouts for all the I/O ports, and the power circuitry. Doesn't include the DAC, doesn't include the TFT display, doesn't include any of the other stuff. It's just a breakout board for the microcontroller, so that if you want just that, that's available for you. And it's significantly smaller.
Is that breakout board require through-hole TFT, or I'm sorry, a through-hole PIC32, or is it like an SMT?
That is, it's the same that it's the PDIP. It's the same one that we use on the big board. If you want something different, you can certainly lay out your own PCB. And in the past, we've had groups that have created their own PCBs for their projects. You just have to account for the lead time associated with getting that board fabricated. So if you want to make your own printed circuit board, you should probably start that like now. Other questions? Okay. So what I want to start with then is I've had some questions about on the lab write-up. I have had some questions about, where is it? This line here. So in the lab, you're asked to put two pieces of information out through the DAC so that we can look at it on the scope. One of the things that you're asked to put out through the DAC is your ADC measurement. And keeping in mind, by the way, I mentioned this previously, 12-bit DAC, 10-bit ADC. So consider left shifting the ADC measurement by 2 bits. Might as well fill up the most significant 12 bits of the DAC rather than the least significant 12 bits. Doesn't really matter, but you might consider doing that. But you're going to put that out, and you're also going to put out, we talked last time about the PID controller. The output of that PID controller is a PWM duty cycle. So every time you interrupt 1,000 times a second, you're calculating a new PWM duty cycle. And we're asking for you to also output that value to the DAC, but to first put it through a low pass filter. And in the lab write-up, we provided this code, which implements a very simple low pass filter. And I've had a lot of people ask, why is this a low pass filter? So I thought we could take just like a couple of minutes to talk through why this is a low pass filter. And in order to do that, I'm actually gonna write on the chalkboard. So let's do this. And I will also stop sharing my screen. Okay. So why is that a low pass filter? Well, let's take a look at something that we can hopefully all agree is a low pass filter. So suppose we have a resistor in series with a capacitor, which goes to ground. So this is R, this is C. Here we have V in, here we have V out. So just like your RC low pass filter from intro circuits, right? We all agree this is a low pass filter. Well, these are in series, which means the current through the resistor is the same as the current through the capacitor. So the current through the resistor is going to be what? It's going to be V in minus V out over R, and the current through the capacitor would be, make sure I get it right, C times dV out dt. We all agree with that, right? Okay, so then we can rearrange this and solve for dV out over dt. So that means that dV out over dt is equal to, let's see, 1 over RC times V in minus V out. Right? So this is kind of starting to look like that digitized version that we were after. All that remains really is to discretize this, which we will do in the following way. So V out is a function of time. So let's call V out at some time t. We'll designate that as we'll say V, how do I want to label it? Vn out a short time later, delta t later. We'll say it's V plus 1. So we're just considering the output voltage at some time t and the output voltage at a small time later, t plus delta t. Now, and we're saying this is Vn plus 1 time step later. At this point in your academic careers, you should look at an expression like this and every muscle in your body is aching to Taylor expand. You just really want to Taylor expand this, right? So let's Taylor expand this. So we say V out at t plus delta t is equal to V out at t plus the first term in the Taylor series, which is 1 over 1 factorial dV out over dt evaluated at t times delta t plus a whole bunch of higher order terms that we ignore. First order Taylor expansion. And we have an expression for that. So we called V out at t plus delta t V at n plus 1. V out at t is equal to Vn plus 1 over 1 factorial is just 1. And dV out over dt is what we solved for over here. So this becomes delta t over RC times V in at t minus, or let me use the labels we've been using, is equal to V in at n minus V out at n. And that is almost exactly the digital expression, right? So in the expression that we were just looking at, this we called, this had the name motor display. This was also motor display. And this was your PWM on time. And we were right shifting this by 4, which is to say we were saying this term here is 1 over 16. Which gives you a low pass filter with a time constant of like 16 time steps, which is what? Fast as compared to the physics of the pendulum, but smooths out a lot of the noisiness associated with the PWM signal. So this is all just to say that we can start from what all of us agree is definitely a low pass filter and arrive at this discretized expression for the output voltage from that low pass filter. And it exactly matches it exactly matches which one? This here. So that expression and this expression are isomorphic to some extent. Does that make sense? Okay. You might experiment with that. Try shifting by 3. See if you like the output on the scope better. Try shifting by 5, right? See if you like that better. Experiment with a little bit, but that is why this is an implementation of a very simple low pass filter. Okay. So the next thing I want to look at then is, let's go back to the PID control stuff. Let me share my screen again. So go back to the PID control stuff. And last time we looked at PID controllers very, what would I say? Qualitatively or phenomenologically, or one of those words, without a lot of math, kind of waving our hands and talking through it. I want to talk through it today with just a little, I want to try to substantiate some of the stuff that we said last time with a little bit of actual mathematical analysis. Not a ton, but a little bit. So I'll just remind you that this is a block diagram of the system that we're considering, right? So what we have is, let's see how to start this. So we have a pendulum, and we're using a potentiometer to read the angle of that pendulum. We're taking the difference between the current angle of the pendulum as measured in ADC units with the desired angle of the pendulum as converted to ADC units, which gives us an error, a current error in ADC units. That error enters our PID controller, which outputs a voltage. It actually outputs a PWM duty cycle, but the motor sees that as an average voltage, right? So it outputs a voltage. The motor is some system that takes voltage as an input and gives prop speed as an output. So you apply voltage to a motor, it transforms that voltage into propeller speed. And we're going to look at the physics of how it does that. But there is some transfer function that describes voltage to prop speed. So the motor starts to turn, and then we have it attached to some pendulum, which is another physical system that transforms motor speed to pendulum speed, pendulum rotation speed, which moves the pendulum to some new position. We sample that position, and we do the whole thing again. So what I want to take some time to do today is to consider the motor physics and to consider the pendulum physics and to substantiate some of the things that we were observing and claiming about the PID controller in the context of the motor and pendulum physics. So let's do that. Let's start with the motor. So what we're going to do is consider the mechanical motor of the mechanical model of the motor. So the model of the motor as a mechanical system. And then we'll consider the electrical model of the motor as an electrical system. That's going to give us two sets of differential equations. We'll combine the two to come up with a transfer function that transforms voltage to rotor rate, propeller speed. So let's consider first the mechanical model of the motor. How can we think about a motor? Well, we can think about it as some inertial mass with moment of inertia J spinning about a shaft. And we are applying some torque to spin that shaft. Meanwhile, friction, which we're going to say proportional with some proportionality constant B, it's proportional to the speed of the shaft rotation, is exacting torque in the opposite. And the output here is some motor rotation angle theta and rate theta dot. So a motor is a shaft with an inertial mass. We apply a torque, there's friction, and the thing turns. So we combine this stuff into a torque balance equation, which is just the rotational version of F equals ma, right? So we have our sum of torques equals j theta double dot, moment of inertia times angular acceleration, instead of force times acceleration, right? So we have our applied torque minus torque from friction equals j theta dot, the rotational version of F equals ma. Is that okay? Oh, is dot notation, do you guys use dot notation? Okay, sorry. So it's just a shorthand. I think it is, yeah. So one dot is to say first time derivatives, so d dt of theta. Let me write it down. Really? I'm sorry, this is my, who did this? This was Newton's favorite notation, I believe. So theta dot is equal to d dt of theta. Theta double dot equals d squared over dt squared of theta. I will update this to change notation to something that's more familiar. Sorry about that. It's just kind of a tidy way to write down time derivatives. So, okay. We have this torque balance equation for the mechanical model of the motor. Then we have this electrical model of the motor, which we've considered already a few times. We talked about how we consider a DC motor. We can model it as a resistor in series with an inductor in series with a generator. And if you apply the Kirchhoff voltage law to that, we can come up with another differential equation that describes this electrical model, which is to say we have our applied voltage minus Ri, the voltage drop across the motor, minus L di dt, the voltage drop across the inductor, minus the back EMF voltage, the generated voltage, equals 0. Yeah. Can the PIC32 calculate derivatives and integrals? You will be approximating those things numerically. So you will use, you will Euler approximate the derivative. So you're calculating the derivative of the error specifically. So you'll take error at time step n and error at time step n plus 1. Like we talked about last time, I actually recommend n plus 4 or so, and computing the difference to approximate the derivative. And then the integral will be a series of, you'll have an accumulating variable for in which you are adding the error from subsequent time steps to add up the total error over time. Yeah. So, okay, so we have our mechanical model of the motor, which gives us a certain differential equation, an electrical model of the motor, which gives us another differential equation. We can look at these two and ultimately combine them. So let's first take a look at, in the electrical equation here, this back EMF voltage. We can make some substitutions associated with that. The substitution being, if you're operating a motor within its limits of operation, just to say you're not saturating the motor, then the relationship between the voltage that you apply to the motor and the speed of the motor's rotation is approximately linear, right? So you increase the applied voltage to the motor a little bit, the motor speed increases a little bit proportionally, right? You apply a little more, it increases by the same proportion. Thrust is nonlinear. We talked about that last time. Thrust is related to the square of the rotation rate, but voltage applied to the motor and motor rotation rate when you're operating the DC motor in its limits of operation is about linear. So we can say, okay, the angular rate of the motor is going to be equal to some constant of proportionality, which we'll call kV times the voltage. So this is an expression that gives us rotation speed as a function of voltage. If we rearrange this, we can get generated voltage as a function of rotation speed, which is that back EMF. Right? So we rearrange this and we say, well, if we divide kV to the other side, then we have V is equal to 1 over kV times the rotation rate. And we note that the particular V in question here is the back EMF voltage. It's the voltage generated as a function of motor rotation speed. And then just to simplify things, instead of having 1 over kV everywhere, let's just define a new constant that we'll call K sub E, which is 1 over kV, which gives us an expression that we can substitute back in for that back EMF voltage. That is now a function of the motor rotation rate. So what we've done is looked at this equation, or this differential equation that describes the electrical model of the motor, looked specifically at the back EMF here, noted that motor rotation rate is proportional to the applied voltage, done some rearranging to get generated voltage as a function of rotation rate, and substituted back in. And then we can think more carefully too about this applied torque. So the applied torque, much like the rotor speed is proportional to the applied voltage, the torque is proportional to the current through the motor. We're looking now at the mechanical model of the motor. We're looking at this torque here. And we're noting that that torque is equal to some proportionality constant K sub tau times the current. So we can substitute that back in for the torque expression tau in the mechanical model of the motor. And then it turns out that if you are working in SI units, these two constants of proportionalities are in fact the same. So the constant of proportionality that describes the relationship between current and torque in SI units is the same constant of proportionality that describes the relationship between applied voltage and motor rate. So we'll just call both of them K, which gives us now two differential equations. This is our updated equation for the mechanical model of the motor. AI is the applied torque, which is a function of current, minus torque from friction equals J theta double dot, moment of inertia times angular acceleration. And electrically, Kirchhoff's law tells us that the applied voltage minus the voltage drop across the resistor minus the voltage drop across the inductor minus the voltage from the back EMF has to equal 0. So we have two differential equations, one describing the motor as a mechanical system, one describing the motor as an electrical system. But you can see that they're related. They both have current as a parameter here, so we can couple them. So in order to do this, we can then take each of these differential equations and Laplace transform them. There's no Laplace transforms. This would have been covered in what? 2100, I guess? Okay. So you'll remember, if you dig way back, you can transform a differential. If you Laplace transform differential equations, it gives you algebraic expressions instead of differential expressions, right? Which makes solving for things like transfer functions a lot simpler. So if we Laplace transform the mechanical differential equation, then we end up with the same constant of proportionality K times Laplace transform of the current, which people typically you indicate these things as capital versions of whatever you're Laplace transforming. So capital I being the Laplace transform of the current as a function of S, minus B times S times Laplace transform of the rotor rate. Remember that when you're Laplace transforming a first derivative, you get an S out front, right? Equals S squared times J times Laplace transform of the motor rate. And then similarly, we Laplace transform the differential equation that describes the motor as an electrical system. Okay, so then we have these two algebraic expressions, two polynomial expressions, I should say. And now we can solve for, by combining these two things, the transfer function, which is to say, the function that takes applied voltage as an input. So it's the function that describes the transformation from applied voltage to motor rate, which we arrived at by rearranging these two equations to solve for theta dot S over Vs, where we said S theta S is equal to theta dot. This represents the motor, the Laplace transform of the motor rate. So this is the transfer function for the motor, for a simple model of a DC motor. What we're going to look at next is the Bode plot for a DC motor. What do you expect it to look like? Yeah. What do you think? Yeah, it looks like a low pass filter. Does it kind of make sense that this should look like a low pass filter? Suppose that we very slowly vary the applied voltage to the DC motor. Then the output rotor rate we expect to track our input quite well, right? Which is to say we increase the voltage and we see a corresponding increase in rotor rate, we decrease it. Which you would also see, for example, in like when you're driving the car, right? You step on the accelerator slowly, the car speeds up, you release it, the car slows down. What if you were to vary the applied voltage to the motor extremely quickly? Maybe through, oh, I don't know, a pulse width modulation signal, right? So we're varying the applied voltage to the motor extremely quickly. What we expect is not for the motor to turn on and turn off extremely quickly, right? It doesn't start and stop crazy fast. What it does instead is average out that extremely fast input, right? It's low passing the PWM input in the same way that if you were to get in your, don't do this. If you were to get into your car and as quickly as you can, go like this on the gas pedal, the car doesn't go 0 to 60 to 0 to 60 to 0 to 60, you know, it low passes your input and you end up going at some average speed, right? Corresponding to the depth that you're pushing the gas pedal. So we expect a low pass filter. And in fact, that's what we get when we look at this. So there's some cutoff frequency here. And above that cutoff frequency, we see the Bode, the amplitude part of the Bode plot roll off like a low pass filter. And in fact, it rolls off like a two-pole low pass filter. So this is falling off at minus 40 dBs per decade. So you will remember that for a two-pole filter like this, we expect at high frequencies a phase shift of minus 180 degrees. About minus 90 at the cutoff frequency, and then it continues to roll down to minus 180. So in terms of modeling the motor, you know, we went through a bunch of work here, or a significant amount of work with some approximations and waving our hands a little bit to try to capture the physics associated with this motor. And we ended up with a Bode plot that looks like this. And what we realize is to a pretty good approximation. Oh, so by the way, if you take that transfer function, you apply a step impulse, which is to say, you know, the motor is sitting here and you apply you say go faster. This is what the step response looks like, which is probably what you'd expect. It sort of slows up, or it slowly creeps up towards what you commanded. We look at these things and it, you know, if you wanted to simulate this to a very reasonable approximation, you could just simulate all that physics as a low pass filter. Say, okay, I'm just going to model the motor as low. It takes my applied RPM command and low passes it, and that is what the motor is going to be modeled as, a low pass filter. And you know, this is the Bode plot for that simple approximation for the motor. This is the Bode plot for the physics, you know, the actual physics, so to speak, and they match pretty well. So you can get away with making sort of this simplifying assumption about the motor, that it basically acts like a low pass filter. You'll also notice the cutoff frequency for the motor is, we'll see this when we look at the pendulum physics, it's quite high frequency as compared to the physics of the pendulum, which is to say that if we tell the motor go faster, the motor speeds up from the perspective of the pendulum basically instantly, because the pendulum is a lot slower than the motor. The fundamental frequency of the pendulum, you you can measure this, by the way. Once you have the DAC displaying the ADC data, have it just hang straight down and bump it and measure the period, its natural frequency. You'll probably find a fundamental frequency of something like, a period of something like maybe half a second or so. Slow compared to the motor. What that means is for our control system, the physics of the pendulum and the resonance of the pendulum is what drives a lot of the control problem. And we can basically, until we get to very high frequency, abstract away the motor. The motor is something that turns on instantly and turns off instantly as far as the pendulum that we're trying to control is concerned. And it's the physics of the pendulum that really drives the control. So let's look at the pendulum physics. And we're going to go through basically the same exact analysis that we went through for the motor, just with different equations. So as before, we're going to set up a torque balance equation here. So the things that are applying torque to the pendulum include thrust from the motor, gravity, and friction. And I'm cheating here a little bit, where I'm just saying thrust is proportional to the am I sharing the right screen? Okay. We're going to say thrust is proportional to the force from the motor times the length of the arm. Remembering that that force is actually nonlinear related to rotor rate. I'm just saying force from thrust so that we can do a linear analysis here, and it's a little bit easier. But that force is actually non-linearly related to motor rate. It's related to the square of motor rate. In any case, so torque from thrust is equal to F times L, because the thrust force is always perpendicular to the motor arm, right? Yes, I do. I mean the speed that the propeller is spinning. Gravity, the direction of the force of gravity, we need to account for the angle of the arm in these torque calculations, right? Once we get up to totally vertical, the gravity is producing exactly 0 torque on the arm, right? Horizontal, the torque is from gravity is at a maximum. So we need to include this sine theta term when we're including a torque from gravity. And friction, similarly to before, we're just going to say is proportional to the rate at which the pendulum is moving. So we have thrust, gravity, and friction. As before, we can set up a torque balance equation here. So we say the sum of all the torques is equal to the moment of inertia times the angular acceleration. And we can, to a reasonable approximation, approximate the moment of inertia as m, the mass of the motor, times the length of the arm squared. We're approximating the pendulum as a point mass at the end of a massless beam. It's an okay approximation. It's not a great approximation, but it's okay. So then we can set up our torque balance equation. So we say the torque from thrust minus the torque from gravity minus the torque from friction is equal to J times the angular acceleration, where we've substituted ml squared for J. And up above, we solved for the expressions for torque from thrust, gravity, and friction as so. We just looked at these. And then we can rearrange this to solve specifically for theta double dot, which is to say the angular acceleration of the motor. And we notice something, which is nonlinear equation. There's a sine theta in there. So for purposes of doing this analysis, let's linearize this equation about theta equals 0, which is to say the motor hanging like this. And you'll remember that for small angles, sine theta is about the same as theta. So we substitute theta for sine theta. Okay. We Laplace transform this equation. And then we come up with a transfer function that takes force from thrust as an input and gives us pendulum angle as an output. And when we look at the Bode plot associated with this transfer function, this might also look familiar to folks. We'll notice that the amplitude response has a maximum at the resonant frequency. And if you trace your hand down, you'll find that that maximum is at about 5.7 radians per second. And you'll remember from physics 11-12 probably that the resonant peak of a pendulum is at the square root of g, the gravitational constant, over the length of the pendulum L. So if we solve that for our pendulum, we get 5.7 radians per second. So that makes sense. So we see the peak where we expect to see the peak. As I mentioned before, you can experimentally determine where that peak is by bumping the pendulum and measuring the oscillation period. You can also, incidentally, the damping of the pendulum is related to the width of this peak. So you could also measure that. But we notice a few things. So first of all, we notice that this too, so at the resonant peak, we have a phase shift of minus 90 degrees. And then at high frequencies, we have a phase shift of minus 180 degrees. Phase shift of minus 180 degrees. Why is this a problem? So currently, right, this is a stable system, but at high frequencies, suppose we have a 180-degree phase shift of our applied input coming out of the pendulum here. Well, then this subtraction becomes an addition, right? And the whole system becomes unconditionally unstable. So right now, we have a stable system. How do we know this system's stable? We can look at the gain and phase margins, right? So we look at where the amplitude crosses over 0 dBs, and we come down to our phase plot, and we see we're at about, I don't know, minus 135 or so degrees, which means we're still at 180 minus 135 degrees away from minus 180. So we're still in a stability zone, but our system's rather slow. How would we increase the speed of our system? We talked about this last time. We add proportional gain. What does proportional gain do? It just lifts up the amplitude part of the Bode plot, but does not affect the phase part of the Bode plot. So suppose we lifted that up a little bit. Let me do this. So suppose we lifted up the amplitude part a little bit. Okay, so now our crossover frequency is here, and you can see that we've increased the speed of the system, but our phase margin is now getting really close to 0. The symptom of this will be as you're increasing the KP value, the proportional gain in your controller, the system will be faster, but you're going to see more oscillation. You're destabilizing the system. If your system has greater than 0 dBs gain at a phase shift of minus 180, it is unconditionally unstable. And you can make this happen. You can make this happen if you increase your proportionality gain too much. What you will see is the motor snapping between saturated high and off. It's going to look like really severe oscillations, but the motor is actually saturating and turning off, and saturating and turning off. And it's because you are driving it in a region of this plot where you have 180 degrees of phase shift. We're out of time. We can continue this next time. The solution, I will just say briefly, a little spoiler alert. What does the derivative part of the PID controller do? It adds phase. Remember that a differentiator adds 90 degrees of phase. So we place that differentiator oh, we start adding the phase maybe somewhere around the resonant peak, and then at high frequencies, it stabilizes the system. It reduces oscillation. This is also why we have to be careful with that integrator term. What do integrators do? Subtract 90 degrees of phase. So your integrator will destabilize your system at high frequencies. So you need to be careful with it. If you turn up that integrator too much, the first symptom will be oscillation. And then the next symptom, as you turn it up higher and higher, will be destabilization. Yeah.
I have a quick question about the EC technical writing.
Okay.
Yes. Wait, what is that particularly? Like, how is this different from like our labs and like the final?
Give me 1 second here. I'm getting confused. I lost my Zoom controls.